Hello, and welcome to the New Mexico Bureau of Geology and Mineral Resources Geographic Information Systems informal lecture series. I am your host, Phil Miller, and today my co-host is Tyler Askin. We're going to be working through the process of building a cross-section profile in ArcGIS Pro using the USGS's Toolbox built by Evan Toms that will make a GeMS compliant profile, segmented profile, and apparent dip orientations. I'm now going to turn it over to Tyler to walk you through the process and use of this tool.
Hi, I'm Tyler Askin, and so we're going to go through four things in this tutorial. First, we're just going to briefly talk about where to find the tool, how to set it up in Arc Pro, and then we're going to talk about how to create the segmented surface profile. Then we'll spend a little bit of time discussing the apparent dip markers and how to build those, and then we'll wrap up with building the cross-section template for the cross-section of the map. So for the example we're going to use today, I have OFGM 83 Leiden. It's a 1 in 24K map, 7.5-minute quadrangle. And so the first thing we want to do is install the tool. So there's a couple places you can find the tool. If you're at the Bureau, you can find it in the O drive, Styles and Standards, Data Models, GeMS Tool Pro, XS Update. It's a branch of the overall GeMS tool, but in order to find it, you just add Toolbox in your catalog. If you're not at the Bureau, or if you don't have access to the O drive, you can find it through the USGS GeMS GitHub, and you can find the tool there, just doing any type of regular search. A few things you're going to want to set up the tool with. You're going to need to make sure that your environments are set up properly. You're going to want to go up to the top of Arc, click Analysis, Environments. Make sure that your current workspace is set to your project and any Scratch database that you have associated with that project. And then something that's really important is making sure that you have the appropriate style file imported for the project. So in this case, it's the FGDC GeMS style file that's very helpful for building the template later on. And then finally, you just want to make sure that you have your folders set up, making sure that you can easily access everything. It does become a pain. You are sometimes navigating through a lot of folders, so it's nice to have those default folders and those default databases set and ready to go, just to make things a little faster. It's a very simple tool. It's just there's a lot of little steps, and it can get a little, you can have complications, but it shouldn't be that bad. So here we have our map ready to go. It doesn't matter, you can have all the features in the map with this tool, and you shouldn't have any problems. But let's see here, sorry. So if you've added this tool to the toolbox, there's a couple ways you can get it from the catalog. You can open it from here, or you can go to your geoprocessing pane, and you should be able to find it here as well because you connected it to the project. The tool we're going to want to run is this project map data to cross-section tool. And here are all the parameters for the tool. We're going to go ahead and select our geodatabase through the File Explorer. We just select Leiden, hit OK. There is an option. You can project all of the features in the geologic map feature class or feature data set. You may want to do that. I don't recommend it because it will project every single feature class, regardless of whether it's important or not. And usually if you're trying to build a cross section, you have specific things that you're trying to target. So, you may not want tick points, map extent poly. So in this case, typical ones that we're going to be dealing with in building a cross section are contacts and faults. You want to see where contacts are on a cross section. Geologic lines, you may want to see where relevant folds and other lineations are. And map unit lines, you may have a marker bed. You want to see where that intersects with your surface profile. And map unit polys, these are good to tell you, what map units are outcropping along your cross-section line right here. So there's our cross-section line, A to A prime. And now we're going to select our DEM. So the way that this tool works is it's going to take a line and it will gather information about the elevation along that line and plot it each one of those elevations as vertices and give you that surface profile line. So for our case, you should have a spatum meters if you want to use meters and not feet. And then section line. So in this case, our section line is our cartographic line. If you have more than one cross-section line, you want to select which one. It should highlight. So up here at the top, we have the edit option. I hit select, and then making sure that you select the correct line. Not have the correct line. But here, there's another option too. Sometimes you can misclick. It's just good. We only have one here. I'm just going to go ahead and select it. It highlights it. So that's important. And then you want to tell it which quadrant you want to start in. So our line starts here in the upper left part of the map. So we're going to select upper left. And then we have our output name token. This is the name of the feature data set that the tool is going to create for your cross-section surface profile.
Hey, Tyler, can I ask a question really quick?
Yes.
Wouldn't you need to create that feature data set in advance of so that you can get the coordinate system to match?
That is correct. So if you choose to create an output name token here without having created it already, it will create a feature data set with an unknown coordinate system. The way to get around that would be to preemptively create the feature data set. And so when the tool runs, you'll name it the same name as the feature data set that you preemptively created, and it will fill that feature data set with feature classes. So in this case, go through here. Now I've already pre-built this, but the way you would do it is you would right-click your geodatabase, and we're going to choose New Feature Data Set. We've selected the database that we want. We're going to give it the name that it's going to have. So I'll get back to this when we get back to the tool, but the tool has an output name token that it will pre-fill with cross-section, the term cross-section. So we're going to go ahead and get around. We're going to be prepared for that, and we're going to create a cross-section A surface profile. Okay, that will be the name of our feature data set. And then we're going to select the coordinate system that we want our feature data set to be in. should be the same as the rest in the geodatabase. In this case, it is NAD 27, UTM zone 13, and a vertical coordinate system. NGVD 29. Okay, and then you run the tool. It'll create the feature data set, cross-section A underscore surface profile. So to go back to what you talked about, and thank you for reminding me that, Bill. That's a step that we just came up with now. So here we go. We're going to target the geodatabase. We're going to select our feature classes. Always, and that's it. You'll notice I'm not including orientation points in this because there's a few steps I'd like to talk about first before we deal with that. Now you could include orientation points if you had already gone through everything else that I will talk about, but for now, we're just not going to include orientation points. We're going to add our spatum meters, our section line, cartographic lines, upper quadrant, upper left. So this is what I was talking about. You'll see it here. The output feature data set will be named cross-section output name token. So we've already added cross-section. So we're just going to call it A underscore surface profile. There is an option to add vertical exaggeration if you would like. For this case, we have no vertical exaggeration. Scratch database, let's go ahead and point that to our Scratch database. I leave save intermittent data unchecked and go through, check if that's something you want to do. Now, in this case, if this is the first time you're building it, it gives you the option to add a surface profile. If you didn't, it would just create a series of segmented lines across the surface profile. It wouldn't give you this, but this is one way you can do it. Also, if you added cartographic lines, that would give you a surface profile too. We're going to add the frame. So we're going to choose the maximum elevation of our cross section. So one thing you can do is you can refer to your DEM. That'll tell you what the maximum elevation available is, but we also want to add a significant amount of meters above the maximum elevation of the DEM because we like to have a little extra space to add the A to A prime labels and the call it the coordinate labels, northwest, southeast, and then giving you some space to capture any geographic points on the map, which you'll see later here. So in this case, we'll go 2,500 max depth, 1,000 meters. Typically, we go to sea level. You could go to, which would be 0. If you wanted to go below sea level, if you had something that you really had well constraints on, just make sure you put a negative value in there, and that'll add that. X-axis tick intervals. So this will create ticks along the horizontal x-axis of your cross section. This can be useful if you want to, give reference to readers of how far things are. We add generic points which show kind of geographic areas along the cross section, but you can add these. And then something we do here, we do about 250 meters for our y-axis tick intervals. So all of these units are going to be in meters. And then when you're ready, you can run the tool. Okay, so we've run the tool. Now we're just going to check what exactly happened because it won't appear in the map frame. It'll just say that it's complete. So we'll check our databases, go to Leiden. Sometimes it won't show up initially. You'll have to refresh the database just to get it to pop up. And that's where it should be. It should be in the database as a feature data set. And there are all of our feature classes, CSA, surface profile, underscore context faults. It built that frame for us. There's the geologic lines, mapping polys. This is going to be something I'll cover later. And then our surface profile. So now that we have that built, we can go to our cross-section data frame and we'll add those to see where everything is. Context faults, frame, lines, polys, surface profile line. And this could be where you could, let's say you're, still working on a map, you haven't finished a map, and you just want to get something printed out really quick. You could start from here. Notice everything is pretty generic. You can see, there's the outline of a frame. There's your surface profile. That's where our mesa is on this map here, just to give you reference. And there's our frame. But we can't make any distinctions between what's happening. Right? There's a lot of lines, but what do those lines mean? So we're going to go ahead and symbolize these lines here in the symbology tab. I'm going to get unique values. And this is where having that FGDC style file really comes in handy because let's say you have a lot of different contacts, a lot of different geologic lines. It's going to say, you can go through, you can manually add a style to each one of these lines. ArcPro does something really interesting. You can match layer symbology to a style, and it'll just batch add the style to our lines. Very important to note, notice all of our faults are oriented in the same way. The tool doesn't recognize the direction of the line. Our fonts incorporate right-hand rule. So it's going to put all of our faults in the same orientation. You're going to want to go ahead and flip these lines to match the orientation of whatever feature it is that you have on your map. So that's just something really important to remember. You can do that, by selecting it. You can edit the vertices, right click, reverse direction. Now, if you do this and for some reason it won't let you edit, odds are check to make sure that you have your coordinate reference system. You may have forgotten to build that feature data set. So it's just good to check properties, spatial reference. It'll say unknown coordinate system here. And that may be why you're not able to edit. That's just a very common problem that I've encountered. And so here's our frame, geologic lines. Let's just go ahead and quickly add some happy little anticlines here. I guess these are not anticlines. So this is that other way I was talking about. You can do things. Profile. Unique values. So with the polys, it's a little different. We're going to choose map unit. And it's going to give each one a color. So where contacts are, it's a line that intersects where the contact is, but the polygon, it's creating the whole surface profile, and the line is the polygon. So let's just go ahead here, format this a little bit. I like to thicken this up a little bit. It's hard to see. Usually do about 3 points. And then you can change the colors to match geologic time if you want. And then another little nice feature is just to make sure you apply a label so you kind of know what the map unit is. And then we use FGDC GeoH font. If you have any special fonts, like Cambrian units or Triassic units, you can get those fonts to show up with FGDC GeoH. And here's our surface profile. So if I turn everything off, notice we have our colored segmented surface profile here. Let's go ahead and turn off map unit polys. There's our line, contacts and faults, geologic lines. Okay, so there's our surface profile line. We want to get this into the contacts and faults feature class in cross-section A. So let's go ahead here. We've selected our line. We're going to load data. Input. Surface profile. Actually, I forgot, you can do multiple things. We'll go ahead and select the frame because these elevation ticks are also in the frame feature class. We don't really want those because we have our own specialized ticks that we use. So let's go ahead and add the frame and the surface profile to contacts and faults. We're going to use the field map to reconcile field differences. These are attribute-less features. If we go back to surface profile frame, it doesn't have all the attributes that we would like. So it's going to be blank. That's okay. Let's go ahead and run the tool. And that should have added our feature classes. Let's go to okay. There we are. A little hairy there. So we have our contact, we have our map boundary line. These are now loaded into the regular geodatabase and are ready to fill in with contacts that you want to draw, and then you can make polygons. We need this map boundary, we need the surface profile. So when we do create polygons, we have something to bound those polygons in. So there we go. Okay. So surface profile and frame, actually frame is still relevant. We can go ahead and put it down at the bottom for later for creating those elevation ticks, but surface profile, not really needed anymore. We can go ahead and remove that. context and faults have been symbolized, geologic lines have been symbolized, map unit polys have been symbolized. Let's go ahead and we'll just create a new group layer for this. We'll call it surface profile or CSA surface profile, just so we can save all of our layer properties. And then you go ahead and share, save it as a layer file. That way it's ready to go for whenever you need it. Okay. And just one thing I do like to highlight, because it's very important. We create a cross section. Our cross section is it's a profile of the Earth's surface, but that can be kind of tricky because we're using a mapping program. So it's good to just know where we are. So I've just gone ahead and added the topographic map. When it creates this tool, when the tool creates a surface profile, it's going to turn our globe into kind of a Cartesian plane, and it puts us near the 0, 0 of it, the center of it. So we're actually here. We're still on the Earth. We're just now using the map in a slightly different way. And you'll notice that when we are right here, if you look right down there at the bottom, the last number are, what is that, our northing? That 0, 0, 0, 9, 9, 9. Well, that's 1,000 meters. We chose to build this cross section to start at 1,000 meters elevation. If I go down, we're going to hit eventually 0. So that's the direct center of this map frame. So it is helpful later on when you're trying to add elevation ticks and trying to navigate. I'm going to hit right here, and if we wanted to add vertices, kind of to orient where you are on this map. So just a little point about that. Okay, so we built our kind of profile template overall. We have not done orientation points. Orientation points are a little trickier just in that there's a few things to consider when adding orientation points, that it does need its own weight just to consider. So we'll go ahead and talk about that now. But first, little definition. I may call something diptychs. We're going to call these apparent dip markers going forward. And here we go. So the typical orientation points, right? Orientation points is kind of an encompass all term. It's just a point in the database that, marks orientation of some feature. It could be a linear feature, a planar feature, but within orientation points, there are bedding inclinations. These are the things that you're probably used to if you're going to make a cross section, a measurement of a bedding plane. We're going to take those and we're going to turn them into an apparent dip marker, or what I may call a diptych on accident. But just know if I say diptych, I'm talking apparent dip markers. So the bedding inclination is X and Y coordinate data, right? Your GPS point, where that point was taken. And it's orienting on an azimuthal rotation, right? 360 degrees. So when I turn this thing, it's going north, south, east, or west. This black line is, just a cross-section line for reference. Now, what we're going to do with this tool is we're going to turn our bedding inclinations into an apparent dip marker, which now is MZ coordinates, right? It's going to be up, down, left, or right on our cross-section profile, and it's going to rotate off of inclination. So when we rotate this thing, we're no longer doing this, we're going up and down. The tool takes into account a lot of math of how to convert this bedding inclination into an apparent dip marker, but we'll briefly cover, we're not going to do the actual math in it, but I'll show you the attributes tables and the fields that you can look at to, assess the accuracy of these points, but they are pretty good. So there we go. Just wanted to cover that first. So before we get into the process, let's see. So the key thing to keep track of is if you're working on a map and you have paleo currents, you have, bedding orientations, you have fault inclination measurements, what is it that you're trying to put on this cross section? The tool will not distinguish any of these points. So it will put all of them on the cross section. If you have a lot of points, it can get really messy and you'll have to, parse through them and figure out what you want. So a little bit of planning ahead is useful when preparing to create apparent dip markers. So we will be messing with the attributes table for orientation points. So I do recommend before you do anything, it's, these are your precious measurements that you've taken in the field. Make a copy of the feature class. So right click orientation points, copy, select your feature data set, paste. And then I have this OP temp. I know it's there. So this is what we're going to use to run the tool. We'll go ahead and open this table. Now, I'll cover this. I'll show what's about to happen later, but something important to note is that the tool requires the strike value of your bedding inclinations. So here at the Bureau, we capture azimuth. Azimuth is the dip direction of a bed, right? So if I go back to our figure here, our strike being this longer line, our dip direction being that smaller tick. So we need to convert at our dip direction back into strike. Some points do require strike and they don't need to be converted. And if you're not sure which of those are, we did create something here in the FGDC symbols data table. You can find it here in the geodatabase. Let me just close this out so you can make sure that you can find it. FGDC symbols. I'll go ahead and open this up. This is kind of the index of all the symbols, not all of them, but the most common that a mapper will use. And we have a field here, azimuth measurement convention. This is where you can find out if your orientation point is measuring off of dip direction or off of strike. So something you could do is you could join this data table to orientation points. Here's our joins field. You can add the join, input field, base it off of the symbol, join it to the FGDC symbols table. It's going to join it with the symbol field in that table. Then you can hit OK. And now you have azimuth measurement joined to our points. So very useful. You'd be joining it to your orientation points temp, and then you can choose to delete any points that you don't want. Or actually, I'm not sure if a definition query would remove that.
You could probably also do a definition query.
And then see if the tool would just ignore the ones that you've removed with the definition query.
It should.
So in this case, we have our azimuth values. So we have our join. We're going to select by attributes where azimuth measurement convention is equal to dip direction and apply. There we go. Okay. So now we have the ones that are all dip direction. We need to change our azimuth into strike. So we're going to go ahead here, calculate field. Oh, that's actually something very important. Something useful later on is to add map unit attributes to your orientation points. Just a convenient thing for later, so you can figure out what the map unit that orientation point is assigned to on the cross section. But so here we have orientation points azimuth. We're going to take azimuth, we're going to subtract 90. Some of your azimuth values, when you subtract 90, will be negative. The tool will still display the diptychs the correct way. So you can load negative azimuth values in. If that does make you uncomfortable, what you can do is you can select the negative ones. You can calculate field, and then you take that, and then you just add 360, and that'll get them back to positive strike values. But in this case, it's fine. We can go ahead and do that. Yeah, and while you're in here, if there are points you don't want, you can delete them, you can remove them. If you're in your, your temporary feature class, it's okay. You'll still have your backup. And then always just make sure you're making backups anyway. Okay, so now our points should be ready for the tool. That was really the only thing, is just making sure that you have strike values in your azimuth field. Same process before. We're going to link our geodatabase, uncheck project all features. We just want orientation points. We're going to select our orientation points feature class. We're going to select our DEM, spatum meters. Choose our cartographic line. Upper left. Output name token is the same. Surface profile. No vertical exaggeration. Now, this is a new option, select distance. The tool will capture orientation points from both sides of your determined distance. So this is 1,000 meters. So the tool is going to scan down this line, and it's going to reach out for orientation points 1,000 meters from both sides of the line. If you have very localized orientations or features and you're trying to keep things in, choose a smaller value. If you're just trying to get any orientation points that you collected, maybe you have a lot of overburden, you have a lot of quaternary coverage that's obscuring some underlying bedding, and all your outcrops are further to the north or south, but that the transport direction that you want to capture on the cross section is right on the line, then you can choose a further out value. But that's something that you got to consider when you're dealing with orientation points or any points, is the distance that you're willing to go to collect them. And then we're choosing our scratch. Okay. We don't need any of the extras because we've already built those with the tool. So now that we have those, we'll go ahead and we'll run the tool. Okay, so same thing as before. We're going to go to our database. We're going to make sure. Here it is. There's our orientation points. Now we will load them in. Let's see what they look like. Let's turn off this stuff so it doesn't obscure. So they are just points. You'll notice they're all perfectly on the line. This is a byproduct of the tool. The original tool may have captured them at their exact elevation, which may have put an orientation point, kind of below or above the line. If you can imagine, let's say you captured, a point in a valley or on a ridge off of the line, sometimes they would float. This tool puts them back to the line. I haven't seen any apparent dip changes from the tool operating this way, but it is something to keep in mind that if you notice that things are funky, that is something that this tool does, is that it adjusts the point directly to the surface profile. So here's our features. This is what I was talking about. Sorry. So it's going to look exactly like orientation points, the feature class from the data table, but it does add a few new fields. So here's our distance from section. That is how far that point is from the line. The azimuth, local cross-section azimuth. So I think this is the azimuth in relation to the line, but there's our dip direction. And then it turns that into an apparent inclination based on the obliquity to the line. And then if you did choose to vertically exaggerate your cross section, it would take that into account, and it would, if you vertically exaggerate a cross section, it will vertically exaggerate the inclination, the dips of your points. And so this is really this field right here. This is important. The plot rotation. This is the final value that you're going to use to rotate your apparent dip markers to. So here's what we'll do. We'll take our rounded point and we'll give it some type of feature. I have a couple of favorites that I've made, but any linear feature will do, because you're just trying to get it to show the dip. So we've chosen the arrow here. Gallery, let me make sure. Yes, okay, so here we are. So you'll go back to the symbology tab, the kind of main window here. We're going to choose these two squares, very symbology by attribute. We're going to adjust the rotation because you'll notice that they're all just sticking straight up because they're not associated with any field. This is how your map orientation points work. They work off of azimuth, but we're going to choose plot rotation and we're going to choose geographic. And now they're starting to look like regular orientation points where they're dipping down into the ground, right, as beds. And then you can choose to label your inclination. Turn on label. There you go. And now you can kind of know which one is which. So say we do have some -999. And like I said, the tool, yeah, so the tool will take any point and throw it on there. You may not want aeolian features, right? Or paleo currents. What you want is bedding or fault inclinations. But mostly the bedding. Most mappers usually just want the bedding. So this is where you could just delete the unwanted ones. And then this is also why it's nice to have the map unit assigned to these points, because if you took a measurement away from the cross-section line and the tool may not do it for this one, but let's say you have a lot of, quaternary outcrops here, but you were in a valley where you actually did have, bedrock that you were able to measure. It's not obvious from the cross section. So this is just something to think about, how you want to symbolize or label these features as you create these things. But this is done. You now have a ready cross section template to map with. Now, the GIS team, we do a few extra touches to these cross sections. We do a few extra touches to these cross sections where we add, the A to A prime, let's see here. We'll get to the generic points here if I can show it. Oh, that's weird. Why is it not? Oh, because I don't have anything turned on. Yeah. So we add, A to A prime, northwest, southwest, all these feet elevation ticks, meters elevation ticks, just to make it easier for people to read. And so we can add those here. That's why we have that frame with the elevation ticks. Yeah, so that is building a cross section. And I guess if anyone has any questions, feel free to ask. Not hearing any?
Excellent. I'd like to thank you all for joining this meeting. I'd like to thank the New Mexico Bureau of Geology and Mineral Resources for allowing us to do these informal lecture series recordings. It is helping us to communicate our process to our mappers and a lot of the rest of the team and help get the information out to many other users far and wide who need this information. I'd like to thank the Mike Timmons, the director of the Bureau, for allowing us to continue to do this, the GIS services team, Tyler for putting together this presentation, and thank you all for joining, and we'll see you on the next one.